So welcome to seminar this week. I'd like to introduce our speaker, Gongjun. He's an associate professor of statistics and psychology at the University of Michigan. He does a lot of very exciting work in psychometrics, which was very popular in Illinois, so I've seen a lot of his papers previously. Specifically, he works on latent variable models, statistical learning and inference, high-dimensional statistics, semi-parametric models, and survival analysis. He's also a recent recipient of the Top Emerging Leader Award and the Psychometric Society's Early Career Award. So very excited to see what he has for us today.
Okay, thanks for the introduction, and thanks for the invitation. It's a great honor to visit here to meet the faculty and the students. As some of you know, like Xianyang and I, we were like undergraduate classmates. We went to USTC like exactly 20 years ago, so time flies very quickly. So I have also like met like Raymond during our PhD time at my first GSM meeting. That's like also like 12 or 13 years ago. So it's great to visit, meeting with the old friend and the new friends. Today I will introduce some of the new work on this covariance adjusted generalized vector analysis. So motivated by some applications in this educational testing problems. Okay, so this is a joint work with two of my PhD students, Jing Ouyang and Chengyu Cui, and my colleague Kim Ming Tan at the Department of Statistics, University of Michigan. Okay. So some of you maybe know like the topic of psychometrics, some of you may not. So let me give a short introduction of this psychometrics. So actually, it's very closely related to our statistics. It's a branch of psychology where the goal usually is like to want to do this psychological measurement. For instance, trying to measure like individuals like latent traits. So here are some examples. One popular example we may say is like to measure like this IQ, like this general intelligence of people, right? So that's something like or like you want to measure this student's ability, mathematics ability or statistical ability, right? So that's their goal. So it's like essentially it's like a measurement problem. So they have a goal they want to measure. It's like just like this physical measurement problem. We want to measure a people's height, right? A people's weight. So we have this instrument to measure that. But for psychological measurement, the issue is these goals that you want to measure, they are latent. They are not observable, like your ability, we cannot observe that. So they typically, the instrument they want to use would be designed these questions or like, these, so for instance, we often use this standardized test to measure this individual's, education, ability, for instance, like the SAT exam, GRE exam, right? So everyone knows that. And for, also we have this listening test for these medical lawyers, these types of tests trying to measure these latent skills, abilities, and so on. Now, of course, when we're talking about this measurement, we would have an issue like we have like this individual responses to this design question. We would have errors and randomness, and that's like where we need like statistical measurement models. And to help us to use the observed responses to make inference on this underlying not observable latent traits, latent variables. So very naturally, these latent variable models will be kind of used in this kind of psychological measurement problems. So as we explain here, like since the very beginning, actually it's very nicely coupled with the statistics for the for the psychometrics field. So one of the founder of the psychometrics is like Francis Galton. Many of I believe all of us we know him. Like when we're introducing a regression to our students, we often mention his name, who termed this regression to the mean and introduced this correlation, all these concepts. But on that, and also Dr. Galton, he also actually was the founder of the psychometrics field. He was trying to use these design questions to measure these people's intelligence, right? And that started this essentially the psychometrics field. And later on, Charles Spearman, around the 1900s, he developed this factor analysis model. Okay, so factor analysis model is also one type of popular dimension reduction types of tool in statistics and machine learning, and it was introduced started from a psychometrics field, but now of course becoming popular in stats, machine learning, econometrics, also many other fields. And as more people are getting involved in this field in around the middle of 1930, a couple of psychometricians and statisticians, they founded this psychometric society. Actually, it was in 1935, September, and the society was founded at the University of Michigan, actually, in Ann Arbor. So an interesting story is that, interesting note is that one of our largest society, Institute of Mathematical Statistics, was also founded in the same week at Ann Arbor. So some people may join the post. Okay, so it's kind of an interesting historical facts. So later on, people proposed this nonlinear types of factor analysis model, often called this item response theory in psychometrics, which usually is a generalization of this linear factor analysis model, where we usually use these continuous types of latent factors to measure people's ability or latent traits. Now, another popular family of models people use is latent class types of models, where you can review this as discrete types of latent variable models, and many other developments since then. Okay, so now with the goal of doing measurements, an important problem actually is the invariance issue of this measurement, which we also can refer to as the fairness. The problem is here we want to measure this student's ability. Now the measurement invariance means that the response we're going to observe, we want the response only depends on this ability, right? So given this student's ability, the probability of answering a question correctly should then be independent of the other covariance information like gender, race, or others, right? So if this is not the same, then of course we may see there might be some bias for the design questions may favor certain types of group of individuals. So that refers to this measurement invariance, and here we call it it's kind of a fairness problem. Okay. Now, as I mentioned, now if two students have the same ability, then if the questions are fairly designed, then we would expect the chance of answering this question would be correctly would be the same. Now, on the other hand, if the chance of answering this question correctly, they are not the same for two students with the same ability but different kind of background information, then we may say these questions are not fairly designed. And for those questions, introducing such kind of not introducing such types of not equal probability distribution of the responses, we call this as the biased questions. Okay, so here we often call these questions as our items. Okay, so these are those biased items are what we want to identify. So that's essentially the goal of our study here. Now, actually, this fairness issue has a long history. So even though we know nowadays this fairness is a very popular topic in machine learning and many fields, but in psychometrics this issue has been a big concern about 50 years ago. At that time, UTS was sued by an insurance company for racial bias in listening tests for insurance agents. In particular, they claim UTS they favor white applicants over minorities. Okay, so this lawsuit got settled out of the court in the 80s. But since then, UTS have been kind of developing safeguards to avoid those kind of biased items in the test that they provide. Okay, and this affects a lot of not just the students, but a lot of many other occupations and millions of people since then. Of course, nowadays, with this new developments, this fairness issue, we can see in many places over the news. Or different studies, not just in education testing, but in general education and many other fields. Okay, and with the development of these new measurement tools, of course, we also have these new challenges in ensuring this testing fairness. Okay, so this will be kind of the question we want to address in this talk, and the model we're gonna use, which is this item response theory model, which essentially is like a generalized linear factor analysis model. So here, factor analysis model, the linear factor analysis model is, I think, it's a very popularly used dimension reduction tool. Generalized linear factor tool is a kind of we do some transformation of the main function and then use a similar kind of latent structure to model that. The reason is because for those items, the responses we observe usually are categorical instead of continuous. For instance, like for ETS, these questions use correct or wrong answers. So therefore, most commonly, we have like this multivariate binary responses. So we need to do such kind of generalized linear factor analysis kind of modeling. Now, a popular model used in this psychometrics field, they essentially this latent ability it's a hidden, we not observe, and based on the observed responses, which are often categorical or discrete, we want to infer that, and we use this kind of generalized linear factor analysis model. And next, we can give a brief introduction for that. Now, as we are saying, to study this fairness issue, so we have additional some queries that we're interested, and then we want to know, like given this ability. Given this ability, whether these additional queries would affect our responses, right? So essentially, using the graph illustrating, we want to know whether the dashed line they are there or not, right? So if they are there, then that means there are some additional bias for that item. If they're not, then that means the item should be okay, right? So this is also called the differential item functioning in the psychometrics literature. So for an item that have this solid kind of edge from this background information to this item, then that means like now, conditional on durability, you have some additional effects of this direct effects of this covariance to this response. So therefore, we would say this item one here is biased, right? This and also called this diff item. And our goal then is to identify these edges, right? Identify this as whether they are like exist or not. Okay. So next, we formally introduce the model. Now here is some additional notation. So we will use I to denote the subjects such as students, examinees, and we assume we have capital N number of individuals. And we assume that like a capital J number of questions, and we use small j to denote to index those questions. And as mentioned, so we have the responses that are often discrete, so like a binary responses. But here we can see the general setting, where we allow use Yij to denote the ith individual to the jth question. They could be discrete or continuous. So we are modeling this under this generalized linear model framework. Okay. Now, just as a generalized linear regression model, here we do a transformation of this main function of our response given this covariance and the latent variables. Now, a commonly used link function could be logistic, orbit, identity link, and so on, right? Now, furthermore, some notation here we use X to denote those observed covariance of interest, like this gender race or this or group country group informations, and we use theta here to denote the latent variable corresponding to the latent abilities, for instance. Okay, so here the latent variable is a k dimension, and the number of covariance is a p dimension. Now, in this study, we're gonna consider this number of factors as a fixed, and we allow this p kind of growing large theoretically, but then we will see some details later. Okay. All right. Now the modeling here, if we know this theta, then that's just like a generalized linear model. Now, what makes it different from this generalized linear model is like this theta, they are not known, right? So these are like latent factors, right? So that makes this covariance adjusted like a generalized linear factor analysis model. Now, for the covariance, beta here for the X, then that's essentially corresponds to whether we have a covariance effects given conditional on these latent factors. Now, if you want to know whether an item is biased or not, essentially here we are kind of doing this statistical inference problem of testing whether this beta j is 0 or not, right? And this alpha, then following the factor analysis literature, that's the factor loading vector for this jth question, right? So now this the factor loading and this covariance effects. Okay. Now using this graph to denote this, when this beta essentially corresponds to the effect of this dashed line, and we want to know whether they exist or not. And this alpha corresponds to this solid line from theta to y. That's like the factor loading, where theta is not observed. Okay. Okay. So in summary, now our problem is like we observe those responses y. We can use capital Y here to denote the response matrix of any individual to j questions. And based on this response y and observed covariance information of interest, which is X is n by p matrix, n individuals p covariance, and we want to infer the rest, right? Including the diff effects, which is whether an item is biased or not. Those beta vectors denoted as this B matrix for all the questions putting together. And also for the latent factors, for each individual, you have a latent factor, and putting together you get this theta matrix, and also this factor loading, which is also unknown to us. Okay, so we want to estimate this B, theta, and A quantity based on Y and X we observe. Right. Right. So now this the model we introduced here actually, and it's not new, right? So it's just this generalized linear factor analysis model with additional covariance, and people have been using this to study this difference effects in psychometrics literature. But now to test whether these betas are zero or not, there are still many challenges for nowadays methods. So one type of method people use in early days is using this anchor item approach. That is to say they may use some domain knowledge to identify some questions that they believe they are not biased. So therefore, they know for these questions, these betas they are zero. So therefore, and they use these types of information to help us to estimate the theta, the ability, and estimate the rest of the beta. And then you can do likelihood ratio test for the beta and so on. The reason we need such types of information is because here we're going to explain in a moment. We have some identifiability issues. If you just directly do estimation, this ability and this beta, they are not identifiable.
The last two slides, there is XI. This I stands for the observation rate, and the called XI. I stands for like the ith student, ith individual, right? So that's the observation.
Yeah, XI is like observed, right? XI, for instance, is so here this plot is showing a plot for one individual, which is the ith student, for instance. Now, XI corresponds to this student's like gender, race, or some other background information. Y corresponds to yi1 to yij corresponds to this ith individual's response to question 1 to question j. So
one kind of maybe more general setting is like x1i, x2i, x3i. This kind of small.
Yeah. You could do that. Here is like for simplicity, I just putting all the p-dimension x in this one box. But of course, you could just do this as this y. You can put like them separately. Here is just for simplicity. Yeah. So here I just I do this just for simplicity. I'm putting all the px's together. But the idea is you could do that one. Yeah. Just here just for simplicity, I just using this way, right? So here x is a p-dimension. So yes, that's a good question. So just to clarify here, x is a p-dimension. So each of these beta is a p-dimension. And the theta here is a k-dimension. So it's all these they are multi-dimension. I only like separated the y. So this y this kind of unit dimension for each question. Okay. Okay. So we need this kind of anchor question constraint because we have this identifiability issue. Because this ability we are not observed, and this ability and this this covariance they could be correlated. Due to this correlation and the latent variable issue, so we have some identifiability issue. We need to put certain constraints, and that's why early days people use this kind of anchor item kind of method. Now, but mentioning here very naturally, you would say, okay, this is like kind of like we are under this model, we want to kind of learning the sparsity structure of those betas, right? So we could just add a penalty in just estimate that. Yes, that's also, people have also done that types of approach. It's like adding adding like this penalty regularization for those betas. Essentially, it's like we are learning the sparsity structure of those betas, right? So we can add penalty and do that. That's also have been done in the literature, but the one issue is that usually, this statistical inference is quite challenging, right? So we know, like, without, latent variable, there are a lot of recent works on making statistical inference, like debiased, lasso and these types of approaches. But here we have latent variable involved. One issue is the identifiability. The other issue, is like how to make inference, because we do want to do hypothesis testing, like make like this analytical quantification instead of just doing this sparsity estimation. Okay, so that's some other challenges that we're gonna address in this talk. Okay, another, this is summarizing what I just mentioned. Another issue, is that nowadays we could have this large scale testing problems. Here is one example of this PISA study, which is like every 3 or 4 years, and involves like about 80 countries or regions, and more than like 600,000 participants, attend this, for this international assessment. And for the assessment, it have like around 500 items. So, it's not like a large scale as many this deep learning studies, but in education, this is kind of a large scale, right? So compare with this classroom types test or like this types of test, this is kind of a large scale testing. Now, for this kind of large scale testing estimation, also have some challenges, is because traditionally for latent factor analysis model, usually these latent factors we model as like random effects. Right, this is kind of like the statistical literature, like the random effects model. For the latent factors, we model as a random effects. There is a population level kind of distribution, and then now the common way of doing likelihood-based estimation then is like we do maximum of this marginal likelihood of integrating out this random effects. Right, now this comes to the issue, like we need to do the integration, and we don't have a closed form. Particularly for linear factor analysis model, we know we have closed form, but for nonlinear factor analysis, we don't have a closed form like the binary responses, right? So we don't have a closed form for this. This introduces the challenges for the estimation. It's just kind of like similar for this, this mixed effects types of model.
Factor model setup, usually there is a rotation that is lurking around. Would anchor items take care of it, or?
Yes, there's some rotation issue. That's like the identifiability issue. I just kind of mentioned exactly. Yes, I will talk more about that. This anchor item types of approach, kind of helps address that. That's kind of like putting certain constraints, so therefore you would not have this rotation identifiability issue. So I will talk more about that, in a few slides. Oh, so here is like I'm just using a general notation. It's like it could depend on x, right? So I'm just again it's a simplified version of this. So this mu x means like this mean could depend on x. For instance, the x could be like a student from different groups. Now this mu could be group specific, or like the sigma could depend on the group. So here I'm using the index x to denote this mean and variance could be depending on the x, because commonly, these covariance information and your ability, they may be correlated, right? They may be correlated. So that's the kind of introduces this identifiability issue in certain sense. Okay, now the integration could be, challenging in this large scale kind of analysis. So one way actually to address this is like just to do a fixed effects estimation. It's just like we know like if you treat this random effects as fixed effects, then the estimation would be much easier, since you don't need to handle this integration, to get the marginal likelihood. Instead, you can just work with the complete likelihood, like the joint. People also call this a joint maximum likelihood estimation. So now, if you treat these latent factors as fixed effects, then this the form is much easier. You don't have this integration. It can be easier for computation. Now this can is popularly used for high dimension kind of data, because for this low dimension where the sample size goes large, the number of questions is fixed. We know this if we do this estimation is not consistent, right? This is a well-known like Lemon-Scott phenomena. Intuitively, it's like if a student only answers a limited number of questions, you can never like accurately estimate this individual's ability, right? But for the large scale type to setting, when J, the number of questions an individual answers also goes large, then you don't need to do integration in your marginal likelihood estimation approach. You can just do fixed effects. You can still guarantee consistency. Again, intuitively, if an individual answers a large enough number of questions, then you can just based on this individual data to do estimation to get like a consistent estimate, right? So this this approach has been popularly used for this factor analysis model for high dimension types of data, like in statistics, psychometrics, econometrics, and genetics, and many other fields in these recent years, right? So they find out for the high dimension data, usually they don't do integration. They just do this that's all like for linear factor analysis model, then just the matrix decomposition. That's much easier than you do the integration and estimate the marginal likelihood, right? So that's being commonly used. But the issue is most of the study they focus on linear factor analysis model in the literature, right? So with the factor only, all covariates are adjusted. For nonlinear factor analysis model, the study is much less. Recently, there are some works on using these factors, but there is a kind of a ULS for studying these types of model when you have a covariates, additional covariates involved in the model, and particularly for doing statistical inference. So that's a kind of the part we're going to focus on in this talk, right? So as I mentioned, in these high dimension types of large scale data setting, when the number of individual and the number of questions both goes large, this double asymptotic regime and the non-linearity issue of the model introduces some challenges. And also, as I mentioned, we have this identifiability issue because the latent factors are not observed, and this could also be correlated with our covariates. And there's a very limited influence result for such types of covariates. So that's the nonlinear factor analysis model. And in this talk, that's what we wanted to address. Okay. So in particular, we're gonna do this joint likelihood-based estimation. So computationally is more efficient than you do this integration in marginal likelihood-based approach. And we don't need anchor item, and we will provide valid statistical inference for the estimation results. Okay. Now here, let's recall this is the problem setup. We observe these responses and the covariates of interest. We want to know whether these betas are zero or not. And in many education psychometrics problem across these latent factors itself is of interest because that corresponds to individual's ability, right? This is of course of interest itself. So for some of the applications where this factor analysis is used just for dimension reduction or adjusting for arithmetic confounders, usually the latent variable itself, the interpretation is not much of importance. But here, like the latent variable itself is of interest. So therefore, we additionally want the identifiability for not just for beta, but also for these latent factors. That corresponds to the question just asked. For traditional factor analysis model, we know there's a rotation issue. So here we're gonna address this propose certain identifiabilities to conditions to handle that. Okay. All right. So we will start with this model identifiability issue. So as we know, identifiability means for two sets of parameters, if they give you the same distribution of your observed data y, then these two sets of parameters should be the same, right? So this is the identifiability. Since otherwise, if two sets of different parameters give you the same distribution of your data, then that means with the observed data, you cannot uniquely identify your model parameter. So it's not identifiable. You cannot have consistent estimation. Of course, you cannot do statistical inference, right? So that's usually, identifiability would be the first thing we need to ensure for consistency estimation and making statistical inference. Now here, the first identifiability issue for the model we consider here is that now if we do a linear transformation of beta, okay, and we introduce a new beta tilde here, which is the linear transformation of the beta involves the Q, which is just a transformation matrix. Psi is the K by P, and alpha is the loading. Now, then similarly, you can define a new theta such that now these two, they will give you the same output. So therefore, now that means the first identifiability issue is up to this transformation of the beta of this T alpha transformation. And similarly, correspondingly, it's like theta is also not identifiable up to this TX transformation. This essentially a question.
So when you have an assumption of you have a distribution assumption of theta.
So
if you theta plus TX, would that alter the distribution assumption?
So here we are not doing these random effects. So we are doing these fixed effects. So we don't put assumptions on the distribution of theta, since we are treating each theta as a parameter. So we don't put a distribution assumption on these thetas. Right? So that's a kind of for computation efficiency, right? So because once you put condition of when you put the distribution for theta, then that becomes like the random effects model for likelihood estimate. You need to integrate out. That's involves the challenges.
So the question about the interpretation of theta, so you're now treating the theta as fixed effects. And so when we interpret them as ability, your theta is k-dimensional. So like, how do I interpret the k coordinates of theta and compare to individuals?
Yeah, so this could be like for instance, later we will see some example. You could have some different types of questions. For instance, in the example we'll show later, it have like 3 different components. Maybe some question about reading, some question about mathematics. So there are like people then. For that case, for instance, they could introduce 2 dimensional factors. One corresponds to your general mathematics ability, another one for your reading ability, for instance, right? So this ability could be correlated, but they correspond like to these 2 different kind of directions, right?
But that's an assumption, right?
Yeah, that's an assumption. So that's a kind of an assumption, but also that's kind of for these types of application, one thing that's different from some others is that this is because the beginning is like the measurement problem. We want to measure this ability, reading ability and mathematics ability. So we start with their score and then design these questions. So it's not like in the exploratory data analysis setting, we have data first and then we do dimension reduction and find the interpretation. While for many of the applications, it's like they have the target first, and then we design is like we design these questions and then collect the responses. So it's kind of like not fully in the exploratory kind of dimension reduction kind of setting, right? So they have some domain knowledge like putting there. Yeah.
Would there be interaction between the questions? Like would one question?
Yeah. Could be. So could be. So that's like the loading. So if we go back to the model here. Right, so the loading factor loading essentially depends on how this question depending on the latent factor. If a question maybe only depending on some of the latent factors but not all, then this alpha could be a sparse, right? Or like if it depends on all the latent factors, this alpha could be every component being there, right? So that's kind of how they do this. So therefore, in this education testing setting, this alpha itself is also of importance because alpha essentially has the interpretation of these questions characteristics. For instance, the difficulty level of this question and how this question related to different kind of scale you want to measure and how this question is the differentiation ability for different scales, right? So therefore for there, like these factors and this factor loading, they are all like they want to all of them to be identifiable for the interpretations they for the interpretations.
Theta is a fixed effect. In this setting, I can treat the theta as a parameter, so graphical state space model, right?
Yeah. So here theta we are treating as effect in the parameters. Yes.
The graphical state space model.
Yeah, I think so. You can think that way. Yes. Yeah, or like it's like this factor analysis, but not factor analysis, network modeling, right? So you have this latent space modeling for network. There often this latent factor is like treated as parameters as well, right? So unless doing innovation way, of course, that's a different story. Yeah. So therefore, this just another note. This types of model actually have very nice connection with this latent space model for network types of data, right? So essentially, here is like a hypothesis kind of a network. You have individuals, you have questions, and then if answer correct or wrong, that's essentially whether there's a link or not. So therefore, this types of model is kind of a very natural connection with this network data, like latent space models.
So when you are assuming theta to be fixed, then that means the correlation between the responses that is totally going to be explained by the correlation between the covariates, right? So is that assumption restrictive or that's kind of wrong?
It will be depending on both. So you mean the response Y, right?
Yeah, so if you go to the next slide. Yeah, the next slide, yeah, so here. If I look at, say, the correlation between two sets of G expectation. Yeah, so G expectation Yij.
Mhm.
So then, okay, wait a second, so.
Yeah, so it's depending on this theta. So yeah, it's essentially it's like we can consider like you are conditional on all the thetas. You can if you are there is a hypothetical distribution of theta, you can consider what we are doing here is like conditional on the theta distribution. That's why as x, right? So for regression, we can also do random x or like a conditional distribution of y given x. So here is essentially we're doing something that is like a conditional on theta and x. We're doing like conditional inference, right? Or like you're treating at the fixed parameters. But you can also understand that it's like we're conditional on the thetas, right? So that's a so this is like the first issue. Now this is actually, it's related to the graph we showed earlier. It's because x and theta, they have this dependence. So therefore, this transformation you see here for the theta particular, essentially is like you are putting some information of x to theta. You're changing the correlation of x and the theta. So therefore, you have this first identifiability issue, right? So it's like, in other words, if you know x and the theta, they are uncorrelated, they're independent, then this would not be an issue, right? Because you do this transformation will make this transform if theta and x they are uncorrelated. If you do this transformation, then after adding tx then become correlated, right? So if you have information that are independent, then this identifiability is not there. The main issue of this is like theta is not observed, and the theta could be correlated with x. So therefore, we have this issue. And another identifiability issue is what we just earlier mentioned is this traditional factor analysis rotation issue, right? So for the factors, which is theta and factor loading, if you put any G inverse G, like invertible matrix here, you get the same result. So therefore, that's kind of the rotation issue for factor analysis, right? So and similarly, you put it here. Now that's the second identifiability issue. Now I want to mention that for the second transformation of the factor issue, it's actually even though you change your t, change your alpha, but actually you can see the beta you obtain here would be the same as this beta here, meaning this factor rotation transformation identifiability issue actually does not affect your beta. So therefore, if our goal is just to make inference about the beta, so we don't need to worry too much about the factor, whether the factors are identifiable or not. We only need to worry about this first issue. But of course, practically, people also have interest of these factors and factor loadings. Then we need to worry about these factor rotation issues, just as other factor analysis literature. All right, so that's this issue we're going to address. For the first issue, we're going to propose some practical conditions to ensure this theta, this beta is identifiable. Okay, the condition we propose is based on earlier work, which we essentially use this L1 kind of condition. We assume the L1 norm of the true beta among all these transformation family that we just introduced, this non-identifiable transformation equivalent family. We assume the true beta have the minimum L1 norm. Now this is satisfied if the majority of the questions are unbiased. Okay, so this can be satisfied if this majority, to explain a little bit more. So this essentially holds if the proportion of unbiased item is bigger than some C. C here is some positive constant, right? So in other words, if we consider each dimension of our X for each covariate itself, if half of the question we are unbiased, then this condition is satisfied. So even though we are kind of making some sparse assumption, but we are not like kind of in the sense of the non-zero, proportion goes to zero, like which is commonly used in high-dimensional statistical inference. While here the sparse, we still allow positive proportion to be non-zero. Okay, so that's we could under additional conditions, certain additional conditions to make this threshold bigger than 1/2. But practically, it makes sense to assume most of the questions are unbiased, right? Because for ETS, for instance, those questions are carefully designed, so it makes sense to say, most of the questions they are not biased. The biased items they are like probably less than one half, for instance, right? So that's the first assumption. Now this will help us to ensure the identifiability of the beta. Now the second identifiability issue is like for the factors. Now we can borrow the assumptions in the traditional factor analysis literature. For instance, you could assume there are some like independent kind of structure among these factors. This is popularly used in explanatory factor analysis, right? So we often assume these factors they are independent with each other, right? And then we may, for that one, we still have this rotation issue. Then we could make additional assumptions for the loading matrix. So therefore, kill the rotation issue as well. So essentially, it's like here we call that this G. The second identifiability issue is about this G matrix for the factor transformation, which essentially is any invertible matrix K by K. So we will need here we will have a K square number of free parameters. Essentially here means as long as we put like a reasonable K square number of constraints, then we will not have this issue, right? So that's kind of the idea, right? So like then you could put these uncorrelated types of assumption, or you could just make certain sparsity assumption for the loading matrix that then corresponds to earlier. Like if we have some prior information of the sparsity, then essentially we are putting constraints there. As long as you have a kind of like a K square number of constraints, then you will kill this rotation issue of these factors, right? So here, in the factor analysis literature, people have proposed different kind of conditions to ensure the identifiability, and we could use any of this. Okay, so now we want to point out, for the identifiability condition we consider, if for any set of parameters, we could find a transformation G and T such that they transform after the transformation, they satisfy the condition we proposed, right? So that's a which transformation? You mean here?
Yeah.
Oh, what I want to explain here is that suppose this is theta and beta are your true parameters. Then I can do this set of transformation, and this theta tilde, beta tilde would give you the same distribution of your data. So therefore, you can never identify your true parameter if you don't put additional constraints. So that means this theta alpha beta here and theta tilde alpha tilde beta tilde here, you see theta tilde beta tilde, they are different, but this gives you the same distribution of your data. That's like not identifiable. This means the model here is not identifiable. You cannot, no matter how large your data size is, if we don't put additional constraints, you cannot consistently estimate theta and beta. So that's why, to avoid this first transformation, we proposed these types of condition. So therefore, we can uniquely identify these true parameters. So if the true parameter satisfy this kind of condition, right? So that's essentially, similarly for the second one, right? All right. So now for the estimation, we can because we use this joint likelihood, then we can iteratively update theta and B. So you see, given theta, we know this just becomes a generalized linear regression model. We can just estimate A and B as a generalized linear regression model. Similarly, given A and B, how to estimate theta, that's essentially also generalized linear regression model, right? So then this can be done quite efficiently. And then after, at the beginning, we don't put any constraint, then we are kind of getting a solution in the equivalent class. And then we do transformation, for instance, minimizing this L1 norm, so therefore we get this transformation matrix T, and then we transform it, and then get this D hat, and then we transform the solution we get from the first step, so therefore they satisfy the proposed identifiability condition. And so, we will gonna show this will be consistent if our true parameter satisfy those identifiability conditions. Now, these are kind of some consistent estimation rates. As mentioned, so here we allow P kind of goes into infinity, but in a kind of rather slow rate, because here we don't put any additional regularizations, right? So if we allow P goes much larger, then we will need to put some additional sparsity assumptions for beta and then put some maybe penalty regularization. But here is like we just don't put any penalty, right? Just exactly like a linear regression model. If you don't put lasso or some other regularization, then P to ensure the consistency and normality P cannot go beyond a much large, right? So that's what we have see under this setting, and the rate here is like near optimal, particularly if we look at the theta here. If we consider the oracle case, we know all the factor loadings and all the B's. Then for each individual, we answer J questions. Then by kind of a central limit theorem, like general, this for theta, then that's like GRM question. We get a square root of J consistence rate, right? And now here it's kind of matches the second term, because here we are kind of including all of them together. It's a 1 over J. It's a kind of square of this. Now the first term is coming from the effects of the other terms. And practically, usually we assume N is much larger than J especially for education testing. It's like the number of individuals is much larger than number of questions, right? So therefore, the leading term could be this first term. It's a kind of achieve the optimal kind of rate. And similarly, for the beta, it could be like if you know all the others, then the beta is like one. For each question, there are N individual answers it. If you know all the loading, all the thetas, then you get the square root of N rate. Now it kind of matches here, but up to some additional terms. So it's not exactly sharp, but there are some additional terms. If P is considered fixed, then I think this will be kind of sharp. But if P goes large, there are some additional terms. Now, in addition to the consistency, we also have this normality to make statistical inference. Particularly here, we can show these factors and factor loading and the theta, and these beta, this whether the question is diff or not, they all follow this asymptotically normal distribution. Again, here this P cannot go too large, and this assumption actually is is kind of stronger than the consistency result, because we want like a sharper kind of rate, asymptotic rate, not sharper rate, and we want like more accurate asymptotic kind of characterization.
So here you assume the rank is long.
Yeah, here we assume the factor, the number is given. Right.
If it's over specifiable.
If the factor is over specified, yeah, that's a good question. Then we would have some rank deficiency issue for this factor. The asymptotic I don't think will still hold, right? So if you have this some deficiency issue, rank deficiency kind of issue, right? Yeah. If the factor is over specified, I expect the result for the beta could still hold, right? As we say, but for the factor and the factor loading, it got affected. Yeah.
This strict convergence, you either fix the N and let J go to infinity, or you fix the J, let N go to infinity.
Both go to infinity. So here we allow N and J both go into infinity simultaneously.
So in this situation, for example, the first one, you need to show it uniformly, in the N setting for all the N.
Yeah, so here, this asymptotic result is for individual result. It's not for uniformly normality for everyone. Okay, but we do have some uniform convergence result, like where you could replace the norm here to be maximum norm. We could have some convergence rate control. While for the asymptotic normality, it's not like uniform for everyone, but that's kind of we cannot prove that, but we can prove for individual it has an asymptotic normality. Yeah, that's a good point. Yeah.
What type of assumption do you have on the distribution of X on these two theorems, the covariates?
For X, the assumption, yeah, we have some kind of general like this eigenvalue bound, this type of just a regularity condition for doing regression in similar types of conditions.
Consider like fixed or like X is random in this theorem?
We kind of consider it's fixed, but we assume like it has some limiting behavior. It's just like a linear regression, right? So for linear regression, like ordinary least square, for instance, like we even though we could consider X fixed, but we need some kind of some assumptions on that. Yes, to avoid some corner cases, right? So for instance, like we need the eigenvalues of the covariance matrix to be bounded and, you know, something like that. Yeah. Okay. Okay, so here are some simulation study. I think need to be a little faster. So, you know, we consider like different settings of, you know, the correlation among factors and our predictors. The correlation level, you know, from 0 to kind of 0.7, a relatively higher correlation, and different sample size, a different number of covariance. A factor is rather 2, is not that large, and J is like 100, 300, 500. We are testing these betas. And we consider two settings. First one is rather sparse setting, where for each covariance there are 5 items they are biased, and for the second setting there are like 20% they are biased. So, and we consider 3 different significance strength levels, and we can see our normality result controls the type 1 error pretty well, and also the power, you know, as the sample size goes large, we have increased the power, and the correlation, of course. The signal strength, of course, it matters here. And also, we can see, you know, to the dimension for the covariance from 5 to 30, the result does not change that much. But still, you know, the larger piece, you make it kind of a little bit lower power. And here across sparse and dense, they both perform kind of similarly, right? For dense setting, it's a little bit more challenging as we expected. Next, you know, very briefly, I'll go over this example mentioned earlier for this PISA data. So this data, it has like these 3 domains, you know, the earlier mentioned like reading, mathematics, and the science. So naturally, we use a 3-dimensional kind of factor to capture these 3 sub-domains of the test. And we also collect information about these students. So here, we didn't analyze the full data, so that's the goal of next step. So here we start with a subset, which is those individuals coming from, you know, Taipei, and there are about 6,000 people, 200 questions, 10 covariates, including, you know, this gender, school, stratum kind of information, you know, whether a school is public or not, whether it's in the urban area or not, and we have 3 factors. And another issue here is that we have a missingness for the response, and this missingness comes from the design, because you see we have 200 questions, but it's not kind of reasonable for a student. You ask the students to answer 200 questions in your exam, right? So usually they design this, you know, use this block kind of structure. So for this 200 questions, they may use like 10 different kind of testlets, and for each student, they may answer like 2 testlets or something like that. So instead of answering all the questions, a student may answer only a subset of these 200 questions by design, right? So the other result can be, you know, carried over for these types of miscellaneous setting, and for the estimation, and you know, this we just, you know, focus on those observed data, and we can get a similar result as we establish. Now here is the estimation result. Now this first one is the gender effects. The positive means like is like a male perform, you know, it's favored, and the negative female favors, and that's the questions you know, we identified, you know, using the you know, normality asymptotic distribution, and after, you know, background correction here, we use the background correction control this rate have multiple testing problem. And for the you know, some of the questions it may, you know, make certain sense, like you know, this question is about this bird, the caterpillars, you know, maybe boys is like a kind of more familiar with this kind of caterpillars, and yeah, but of course, in order to ensure whether there's indeed a bias, we need you know, consult with the domain experts to see. But at least we provide a statistical tool based on the data to help us to identify some of the questions that may be problematic. And here is some additional results for, you know, public, whether a school is a public school or not. Another thing here is, like you see, for this biased item, identified biased item based on data analysis, and you see those questions favoring boys, they are more about the science, favoring girls, they are more about like reading. I think that's you know, again, that's something we need to confirm with domain experts, right? So that maybe not be. So the public school versus you know, this private school, and we have I also identified some result and the urban versus suburb. One last thing is like often a question asked you like why we use latent variable here, right? So here we added some additional analysis, kind of a naive comparison of this is the result without using latent variable, just the result. This is the regression of our result response versus this covariance. And you will see the result, it does not make, it's identified very more kind of biased items. So showing in this setting, actually latent factors is something we need to consider, right? So just to illustrate that point. Okay, so here is a conclusion. So here we consider this identifiability condition for the estimation, identify this biased item, and computationally we use this joint likelihood-based approach, and we can do statistical inference. And of course, there's some additional future work to handling this high-dimensional covariance and missingness in the responses, and also in the covariance. And thank you all. Yeah. So.
We have time for a couple questions.
So can you use the assumption that over 50% or 60% of the questions are unbiased, so should have zero bias coefficients to improve the estimation? Maybe help with identifiability?
You mean like this biased item is over 50%, you mean?
So you had an assumption that
yeah,
you need to have most of the ETS items being unbiased.
Yeah.
So can you use that in the estimation and for identifiability?
Yeah. That's why, that is like related to the first identifiability condition we proposed. So if most of the questions they are not unbiased, then the first condition, like this L1 norm, like minimization condition we proposed here is satisfied in that case. So therefore it will guarantee the identifiability of our data. So that's why we that's essentially why we propose this condition here. So this condition, if we have this majority unbiased, then this condition is satisfied. Okay. So and then.
Aren't you saying that 50% of the betas are zero?
Yeah, like 50%. So here is like for each dimension, like 50% beta, they are zero, for instance. Yeah.
You think strength 50% of the betas?
Yeah. Where they are zero or not, we don't know. It's like as long as you know, maybe like 50% there. But if you know that, then of course you could, if you know which question is zero, then that becomes like the anchor item, like approach. Then you don't need like 50. Then you only need a few. Then you can address the identifiability issue. So here, like we don't know where, but as long as you assume, it's like a smart assumption, right? So like we don't know where, but we believe half of the questions are well designed. Then then this assumption is satisfied.
Yes, if your J here is assumed to be fixed, finite, instead of going to infinity, which is kind of a problem, I think, because you don't have many questions for any particular student. Then which part of your result is still valid?
Yeah, so that's a good question. So for our result here, we rely on the assumption that both n and j goes to infinity. So if j is fixed and only n goes to infinity, then to make this valid inference, we will need to do this marginal likelihood approach instead of this fixed effect approach. Let me go here. So you see, this fixed effect approach is inconsistent if j is fixed. And while now you can do this marginal likelihood approach, you use this population kind of distribution modeling for this theta and integrate that out. If the model is correct, then this can still guarantee you can consistently do make inference for theta. Now we can still use the condition of kind of assumption one there to we have an earlier work for this approach where kind of we considered this a fixed setting. I forgot. Here. So we have an earlier work for this, but that's like a classical regime when J is fixed. Yeah, it's better you need to do marginal likelihood approach. Yeah.
So in practice, it's a choice of K based on prior knowledge, or is there a consistent way?
Yeah, so for some applications, you have certain prior knowledge, you have some kind of K, but you could also, use this similar ways as in factor analysis to select the number of factors. Yeah. Thanks.
All right, well, let's thank our speaker again.